You know that picture of the atom you saw in your science textbook? The one with the neat little electrons orbiting the nucleus like planets around a sun? It's wrong. Massively, fundamentally wrong. Quantum mechanics has been quietly rewriting the rules of reality for over a century, and a lot of what you think you know about how the universe works is based on outdated classical models. Prepare to have your understanding of the quantum world challenged. The data reveals a reality far stranger and far more interesting than anyone ever imagined. Less than 1 in 100 physics students ever really grapple with the implications of the double-slit experiment. It's usually just presented as a weird quirk and then glossed over. But it's so much more than that. It's a foundational crack in our classical understanding of, well, everything. Let's examine the setup. You have a wall with 2 slits in it. You fire particles, let's say electrons, at the wall. Common sense tells you that some electrons will go through one slit, some will go through the other, and you'll end up with 2 bands on the detector screen behind the wall, corresponding to the 2 slits. Simple, right? Wrong. What actually happens is an interference pattern. Instead of 2 bands, you get a series of bands, like waves interfering with each other. This is what waves do. When 2 waves meet, they can either reinforce each other, creating a bigger wave, or cancel each other out, creating a smaller wave or even nothing at all. That's why you get the alternating bands of high and low intensity. But these are supposed to be particles, little indivisible bullets of matter. How can a single particle go through both slits and interfere with itself? This is where things start to get unsettling. To try and figure out what was going on, scientists decided to observe which slit each electron went through. They set up detectors at each slit. And here's where reality really starts to bend. The moment you try to observe which slit the electron goes through, the interference pattern disappears. You go back to seeing the 2 distinct bands, as if the electrons were just behaving like normal, predictable particles. The very act of observing the electron changes its behavior. It's as if the electron knows it's being watched and decides to act differently. Now, it's important to be precise here. The detectors aren't physically blocking the electrons or anything like that. The mere act of gaining information about the electron's path is what causes the change. Consider this. Imagine you're throwing tennis balls at a fence with 2 holes. You'd expect some balls to go through one hole, some through the other, and they'd land in 2 distinct piles on the other side. That's the particle behavior. Now, imagine throwing waves at the fence. They'd spread out, interfere with each other, and create a complex pattern of high and low wave amplitudes on the other side. That's the wave behavior. The double-slit experiment shows that electrons can act like both tennis balls and waves. But it gets weirder. It's not just that electrons can act as both particles and waves, it's that they seem to exist in a state of superposition until they are observed. Superposition basically means that the electron exists in all possible states simultaneously. It's going through both slits at the same time. It's not in one place or another, but in a probabilistic blur of possibilities. Think of it like a coin spinning in the air. Before it lands, it's neither heads nor tails. It's in a superposition of both states. Only when it lands, when you observe it, does it collapse into one definite state. The electron is in a superposition of going through both slits until you try to measure which slit it went through. The act of measurement forces it to choose one slit, collapsing the superposition and destroying the interference pattern. This isn't just some abstract theoretical concept. It has real, measurable consequences. It's the foundation of quantum computing, for example, which relies on the ability of quantum bits, qubits, to exist in a superposition of states. Scientists have performed the double-slit experiment with all sorts of particles, including photons, light particles, atoms, and even molecules. And they all exhibit the same bizarre behavior. The larger the particle, the harder it is to maintain the superposition. But the effect is still there. One particularly fascinating variation of the experiment involves delaying the choice of whether to observe which slit the electron goes through until after the electron has already passed through the slits. This is called the delayed choice quantum eraser experiment. The results are perplexing. Even if you decide to observe the electron's path after it has already supposedly made its choice of which slit to go through, you still affect the outcome. If you choose to observe, the interference pattern disappears. If you choose not to observe, the interference pattern remains. It's as if your choice in the present can retroactively influence the electron's behavior in the past. Now, nobody is suggesting that you can literally change the past. The more nuanced interpretation is that the electron's past is not definite until it is observed. The past, like the present and future, exists in a probabilistic state until it is measured. The implications extend far beyond the realm of physics. It challenges our fundamental assumptions about causality, objectivity, and the nature of reality itself. What does it mean for something to be real if its properties only become definite when we observe it? Are we, as observers, somehow actively creating reality? These are questions that physicists and philosophers have been grappling with for over a century, and the double-slit experiment continues to be a source of inspiration and debate. It's a reminder that the universe is far stranger and more mysterious than we ever imagined, and that our classical intuitions, based on our everyday experiences, often fail us when we venture into the quantum realm. Further examination revealed something even more counterintuitive. How is it possible for two particles to be linked in such a way that they can instantaneously affect each other, regardless of the distance separating them? This is the essence of what Einstein famously termed spooky action at a distance, or what we now call quantum entanglement. The concept emerged from a 1935 paper by Einstein, Podolsky, and Rosen, the EPR paradox. These physicists weren't trying to prove entanglement was real. Quite the opposite. They were attempting to demonstrate that quantum mechanics was incomplete. Their argument went something like this. If quantum mechanics is correct, then two entangled particles can instantaneously influence each other. But, they reasoned, instantaneous action at a distance is impossible. Therefore, quantum mechanics must be missing something, some hidden variables that explain the correlation without resorting to spooky action. Consider two electrons created in such a way that their total spin is zero. Spin, in quantum mechanics, is a form of angular momentum. If you measure the spin of one electron along a particular axis and find it to be up, you instantly know that the spin of the other electron along the same axis is down, and vice versa, even if the two electrons are light years apart. Now, here's the rub. Before measurement, neither electron has a definite spin. They exist in a superposition of both up and down states. It's only when you measure one that its spin becomes definite and instantaneously forces the other electron to choose the opposite spin. Einstein, Podolsky, and Rosen argued that this implied that the second electron must have had a definite spin all along, even before the measurement. It's just that quantum mechanics couldn't describe it. There had to be some hidden variable determining the spin, some piece of information missing from the quantum mechanical picture. For decades, the EPR paradox remained a philosophical debate. It seemed impossible to test experimentally whether these hidden variables actually existed. That is, until John Bell came along. In 1964, Bell devised a mathematical inequality, Bell's inequality, that set a limit on the correlations that could be observed between two particles if their properties were determined by local hidden variables. If quantum mechanics was correct and entanglement was real, then Bell's inequality would be violated. In essence, Bell's inequality provided a way to experimentally distinguish between the predictions of quantum mechanics and the predictions of any theory based on local realism. Local realism, in this context, means that an object's properties are definite and independent of observation, realism, and that any influence from one object to another cannot travel faster than the speed of light, locality. It took several years, but eventually experimental physicists were able to put Bell's inequality to the test. Alan Aspect's experiments in the early 1980s were among the first to provide strong evidence that Bell's inequality was indeed violated. Further experiments with increasingly sophisticated setups have consistently confirmed these results. This means that, as far as we can tell, the universe does allow for spooky action at a distance. Entangled particles really do seem to be able to instantaneously influence each other, regardless of the distance. Locality, one of the core tenets of classical physics, appears to be violated in the quantum realm. But what does this mean? Does it allow for faster-than-light communication? The answer, surprisingly, is no. While the correlation between entangled particles is instantaneous, you can't use it to send a message faster than light. The reason is that you can't control which state a particle will choose when measured. The outcome of a measurement is random. Consider our two entangled electrons. You measure the spin of your electron and find it to be up. You instantly know that the spin of your friend's electron, light years away, is down. but you can't force your electron to be up. It's a random outcome. Your friend will also measure a random sequence of up and down spins. They won't be able to discern any message from the sequence because there's no way for you to control it. So, while entanglement doesn't allow for faster-than-light communication, it does have profound implications for our understanding of reality. It suggests that the universe is fundamentally non-local, that there are connections between objects that transcend space and time. It's also worth noting that entanglement isn't just some esoteric quantum phenomenon confined to the laboratory. It's now being harnessed for various technological applications, including quantum computing, quantum cryptography, and quantum teleportation. These technologies exploit the unique properties of entanglement to perform tasks that are impossible with classical systems. But the fundamental mystery of entanglement remains. How can two particles be so intimately connected, even when separated by vast distances? What is the nature of the connection that links them? These are questions that continue to challenge physicists and push the boundaries of our understanding of the universe. And then came an experiment that challenged even that. This kept me up for weeks. The implications of what I'm about to tell you are, well, they're pretty wild. We've been talking about entanglement and how it seems to violate our understanding of space and time. But the story doesn't end there. In fact, it gets even weirder. To understand why, we need to talk about John Stuart Bell and his groundbreaking theorem. Bell was a physicist who wasn't entirely comfortable with the implications of quantum mechanics. He felt there had to be some kind of hidden variables at play, some underlying reality that explained the strange behavior of quantum particles. Remember Einstein's hidden variables from earlier? Bell felt the same. Something guiding the entangled particles. Some instructions set at the moment of their creation. So Bell set out to prove that these hidden variables existed, and in doing so, he inadvertently created a theorem that did the exact opposite. Bell's theorem, published in 1964, is a mathematical proof that places limits on the types of correlations that can exist if the world is governed by local hidden variables. It's not exactly light reading, but the gist is that if certain statistical inequalities are violated, then local hidden variables can be ruled out. Consider this. Imagine you have two coins. Before they are flipped, each coin is prepared in a way that dictates what side will land, face up. One coin is designed to always land heads, the other always tails. They are sent to different people who flip their coin and record the results. When they compare notes, they find that the coins are always opposite. This is correlation explained by local hidden variables. The outcome was determined from the start. Bell devised a test to see if entangled particles behaved in a similar way. If they did, then hidden variables could explain entanglement. If they didn't, then something much stranger was going on. The Bell test involves measuring the polarization of entangled photons in different directions. Remember, polarization is the direction in which the electric field of a light wave oscillates. You can think of it like the orientation of a filter that only allows light waves vibrating in a certain direction to pass through. The key is that the experimenters at each end can choose to measure the polarization along different axes. They don't have to measure the same thing. This is crucial because it allows them to probe the correlations between the photons in a way that wouldn't be possible if they were simply measuring the same property every time. Here's what's wild. When physicists perform Bell tests using entangled particles, they find that the correlations between the measurement outcomes are stronger than what would be possible if local hidden variables were at play. The statistical inequalities that Bell derived are consistently violated. This means that the correlations between entangled particles cannot be explained by any theory that assumes locality and realism. Locality, again, is the idea that an object is only directly influenced by its immediate surroundings. Realism is the idea that objects have definite properties, regardless of whether or not they are measured. Bell's theorem and the subsequent experiments that confirmed its predictions are some of the most profound results in the history of physics. They tell us that our universe is fundamentally non-local and, in some sense, non-realist. Think about the implications for a second. If local hidden variables can't explain entanglement, then what can? The only remaining explanation is that the entangled particles are somehow connected in a way that transcends space and time. When you measure the property of one particle, you are instantaneously influencing the property of the other particle, no matter how far apart they are. This is where things get really strange. It suggests that the universe is not a collection of separate objects. each with its own independent properties. Instead, it's a holistic, interconnected web where everything is ultimately linked to everything else. The analysis continued. Physicists have performed Bell tests with all sorts of entangled particles, including photons, electrons, and even atoms. And every single time they've found that Bell's inequalities are violated. The universe seems to be stubbornly non-local. So, what does this all mean? Does it mean that faster-than-light communication is possible after all? Again, the answer is no. Even though the correlations between entangled particles are instantaneous, you still can't use them to send a message faster than light. The randomness of the measurement outcomes prevents you from controlling the information that is transmitted, but the implications for our understanding of reality are profound. Bell's theorem forces us to confront the fact that the universe is not the clockwork mechanism that classical physics led us to believe. It's something much stranger, much more mysterious, and much more interconnected. Some physicists have even suggested that Bell's theorem points to the existence of a deeper level of reality, one that is beyond our current understanding. Perhaps there are hidden dimensions or non-local connections that we simply can't perceive with our limited senses. The mystery of entanglement and Bell's theorem continues to fascinate and challenge physicists to this day. It's a reminder that the universe is full of surprises and that our understanding of reality is always evolving. These experiments are creating cracks in the very foundations of what we thought we knew. And what lies beyond those cracks? That's the question that keeps many of us up at night. December 1925. Friedrich Hund, a relatively unknown physicist at the time, published a paper with a rather unsettling proposition. What if particles weren't bound by the constraints of classical mechanics? What if sometimes they could simply pass through barriers that should be impenetrable? He called it, rather plainly, tunneling. The concept felt absurd. Imagine throwing a baseball at a brick wall, and instead of bouncing back, it simply appears on the other side. That's essentially what quantum tunneling proposes, but on a subatomic scale. At first, the idea was largely dismissed as a mathematical curiosity, a quirk of the newly developed quantum mechanics. But as experiments became more sophisticated, the evidence began to mount. Tunneling wasn't just a theoretical possibility, it was a real, measurable phenomenon. Consider a radioactive atom. Why does it decay? In classical physics, the nucleus is envisioned as a ball trapped inside a potential energy well. It doesn't have enough energy to climb over the walls of the well, so it should remain trapped forever. And yet, radioactive decay happens all the time. Atoms spontaneously emit particles and transform into other elements. Quantum tunneling provides an explanation. The particle inside the nucleus has a tiny but non-zero probability of tunneling through the potential energy barrier and escaping. The probability might be incredibly small, but over vast numbers of atoms it becomes statistically significant. It's like winning the lottery. Not every ticket wins, but someone always does. But it's not just radioactive decay. Quantum tunneling is crucial for many other processes, including nuclear fusion in the sun. The sun's core isn't hot enough, according to classical physics, to force hydrogen nuclei together with enough energy to overcome their electrical repulsion. Without tunneling, fusion wouldn't occur, and the sun wouldn't shine. This means all life on Earth is fundamentally reliant on this seemingly impossible quantum phenomenon. It's not an exaggeration to say that quantum tunneling makes the world as we know it possible. So, how does it actually work? Well, that's where things get even weirder. According to quantum mechanics, particles don't have definite positions. They're described by probability waves. When a particle encounters a barrier, its wave function doesn't just stop. It extends into the barrier, decaying exponentially. If the barrier is thin enough, the wave function can extend all the way through to the other side. This means there's a non-zero probability of finding the particle on the far side of the barrier, even if it doesn't have enough energy to overcome it classically. The particle essentially tunnels through the barrier, appearing instantaneously on the other side. It's important to note that the particle doesn't exist within the barrier. That is, we can't observe the particle while it's tunneling. It's as if it disappears on one side and reappears on the other, without ever having traversed the space in between. This raises some profound questions about the nature of space and time. Does tunneling imply that particles can travel faster than light? The answer, surprisingly, seems to be no. While the particle appears to pop into existence on the other side of the barrier instantaneously, There's no information being transmitted faster than light. It's more like the particle is simply bypassing the barrier altogether, rather than traveling through it. Let's examine this a little further. The probability of tunneling depends on several factors, including the width and height of the barrier and the mass and energy of the particle. The wider and higher the barrier, the lower the probability of tunneling. Similarly, heavier particles are less likely to tunnel than lighter particles. This is why quantum tunneling is primarily observed with subatomic particles like electrons and protons, and this has practical applications. Tunneling is exploited in a variety of technologies, including scanning tunneling microscopes, STMs. These microscopes use a sharp tip to scan the surface of a material, measuring the tunneling current between the tip and the surface. By precisely controlling the distance between the tip and the surface, STMs can create images with atomic resolution. Quantum tunneling is also important in the design of transistors, the fundamental building blocks of modern computers. As transistors get smaller and smaller, quantum tunneling becomes a more significant factor. Electrons can tunnel through the insulating layers of transistors, leading to leakage, currents, and reduced performance. Engineers have to carefully design transistors to minimize these tunneling effects. The implications extend beyond technology. Some biologists believe that quantum tunneling plays a role in enzyme catalysis, the process by which enzymes speed up chemical reactions in living organisms. It's theorized that tunneling allows enzymes to bring reactants closer together than would be possible classically, thereby increasing the rate of the reaction. Here's what's wild. Even though quantum tunneling is a well-established phenomenon, it still challenges our intuitive understanding of the world. It forces us to confront the fact that the universe operates according to rules that are very different from those of classical physics. It suggests that reality is not as solid and predictable as we might think. The analysis continued. Quantum tunneling is a reminder that the quantum world is full of surprises and that our understanding of reality is always evolving. It's a testament to the power of human curiosity and the ability of science to unravel the mysteries of the universe, one impossible journey at a time. This concept, once considered a mere mathematical quirk, is now understood as a fundamental force shaping the very fabric of reality. So what other impossible phenomena await discovery? Everyone thought the act of observation was passive, that you just looked, but quantum mechanics said otherwise. And a series of experiments known as delayed choice experiments really twisted that concept into something almost unbelievable. The classic double-slit experiment, as we've discussed, shows that a particle can act as both a wave and a particle, depending on whether or not it's observed. But what happens if we delay the decision of whether to observe which slit the particle goes through until after it has already passed through the slits? That's the core question behind the delayed choice quantum eraser experiment. It's a variation on the double-slit experiment that adds an extra layer of complexity, and it suggests that the act of observation can retroactively influence the past behavior of a particle. Sounds impossible, right? Consider this setup. You have a photon source, a double slit, and a screen. So far so good, just like the standard double slit. But then things get interesting. After the photons pass through the slits, there's a device that can randomly either measure which slit the photon went through or not measure it. Critically, this measurement decision is made after the photon has already passed through the slits. If the device measures which slit the photon went through, the interference pattern on the screen disappears. The photons behave like particles, each going through one slit or the other. But if the device doesn't measure which slit the photon went through, the interference pattern reappears. The photons behave like waves going through both slits simultaneously. The mind-bending part. The decision to measure or not to measure is made after the photon has supposedly already decided whether to act as a wave or a particle. It's as if the future choice of the observer is reaching back in time and influencing the photon's past behavior. Let's examine how this is even remotely possible. The delayed choice quantum eraser experiment involves entanglement. Remember that spooky action at a distance that Einstein hated? In this experiment, the photons that pass through the double slits are entangled with other photons. The measurement on these entangled photons determines whether the which-way information is erased or not. The key is that no information about the interference pattern, or lack thereof, can be known until the entangled photons are measured. The measurement of the entangled photons doesn't change what happened in the past. Instead, it changes how we interpret what happened in the past. It's about correlation, not causation in the traditional sense. Think of it like this. Imagine you have two envelopes. One contains a red card, and the other contains a blue card. You randomly give one envelope to Alice and the other to Bob without them looking inside. Alice then travels far away from Bob. If Alice opens her envelope and sees a red card, she instantly knows that Bob has the blue card, even though they haven't communicated. It's not that Alice's observation caused Bob to have the blue card. They were always correlated. Alice's observations simply revealed the correlation. The delayed choice quantum eraser experiment is similar. The measurement of the entangled photons reveals a correlation between the past behavior of the photons passing through the slits and the future measurement decision. So, does this mean we can literally change the past? Not in the way science fiction often depicts. We can't go back in time and alter historical events. The delayed choice experiment doesn't violate causality, the principle that cause must precede effect. It just challenges our classical intuition about how cause and effect work at the quantum level. The implications extend to our understanding of time itself. In classical physics, time is a linear progression of events, flowing inexorably from past to future. But quantum mechanics suggests that time may be more flexible and interconnected than we previously thought. The past, present, and future may not be as distinct as they seem. Scientists discovered that the delayed choice experiments highlight the importance of the observer in quantum mechanics. The act of observation is not a passive process. It actively shapes the reality we perceive. This raises profound questions about the nature of consciousness and its role in the universe. Does consciousness somehow play a fundamental role in collapsing the wave function and determining the outcome of quantum events? These experiments are not without controversy. Some physicists argue that the delayed choice quantum eraser experiment is simply a clever demonstration of quantum entanglement and correlation, and that it doesn't really imply retrocausality or time travel. They argue that the experiment can be explained without invoking any violations of causality. However, even the skeptics acknowledge that the delayed choice quantum eraser experiment is a deeply puzzling and thought-provoking result. It forces us to confront the limitations of our classical intuition and to consider the possibility that the universe may be far stranger and more mysterious than we ever imagined. The analysis continued. The delayed choice experiment is a reminder that quantum mechanics is not just a set of mathematical equations. It's a fundamentally different way of thinking about the world. It challenges our most basic assumptions about reality, causality, and the nature of time itself. And it suggests that the universe may be far more interconnected and interdependent than we ever thought possible. But what happens when we zoom out even further? There's a weird problem that emerges when we try to observe quantum systems. It's called the quantum Zeno effect, and it basically says that if you watch a quantum process constantly, you can freeze it in time. Sounds like science fiction, right? But the experiments bear it out. Here's the basic idea. Quantum particles exist in a superposition of states. Think of our radioactive atom from earlier, which is simultaneously decayed and not decayed. It's only when we observe the atom that it chooses a state. It either decays or it doesn't. But what if we keep checking on it? What if we're constantly peeking to see if it has decayed yet? This is where things get bizarre. The quantum Zeno effect says that the more frequently you observe the atom, the more you prevent it from decaying. It's like the atom is aware it's being watched and it's too shy to change. If you look at it often enough, it will essentially never decay. It's frozen in its initial state. Let's examine a slightly different example. Imagine a particle that has a certain probability of transitioning from one energy level to another. Without observation, it will eventually make that transition. But with continuous observation, that transition can be suppressed. The particle gets stuck in its initial state. This isn't just theoretical mumbo-jumbo, it's been demonstrated in labs using various quantum systems, including atoms, ions, and photons. Scientists have used carefully timed pulses of light to effectively measure the state of a quantum system repeatedly. And what they found is that these frequent measurements can indeed inhibit the system's natural evolution. The evidence shows that the more frequent these measurements, the slower the evolution. It's as if the act of observing forces the particle to keep resetting to its original state. Each observation collapses the wave function, and the particle has to start all over again with its transition. So if you collapse the wave function often enough, you can effectively stop the transition from happening at all. This has huge implications. Consider quantum computing. Quantum computers rely on the delicate manipulation of qubits, which are quantum bits that exist in a superposition of 0 and 1. These qubits are incredibly sensitive to their environment, and any unwanted interaction can cause them to decohere, which basically means they lose their quantum properties and become useless for computation. The quantum Zeno effect offers a potential way to protect qubits from decoherence. By constantly monitoring the qubits, scientists might be able to freeze them in their desired state, preventing them from collapsing prematurely. This could significantly improve the stability and reliability of quantum computers. But there's a catch, of course. Measuring a qubit also disturbs it. It's a very delicate balancing act. You have to measure frequently, enough to suppress decoherence, but not so frequently that you introduce new errors into the system. It's a bit like trying to herd cats while wearing oven mitts. The quantum Zeno effect isn't limited to just preventing transitions. It can also be used to accelerate them. This is known as the quantum anti-Zeno effect. In certain situations, frequent measurements can actually speed up the rate at which a quantum system evolves. It sounds contradictory, but it's not. The key is the nature of the measurement and the specific properties of the quantum system. In some cases, the measurements can effectively nudge the system in the direction of its transition, causing it to happen more quickly. Think of it like this. Imagine you're trying to push a heavy box across the floor. If you push it continuously, it might not move at all due to friction. But if you give it a series of short, sharp pushes, you might be able to overcome the friction and get it moving. The quantum anti-Zeno effect is like those short, sharp pushes. So the act of observation in quantum mechanics is not just a passive process. It's an active intervention that can dramatically alter the behavior of quantum systems. We can freeze them, we can nudge them, we can even potentially control them in ways we never thought possible. This challenges our classical intuition about how the world works. In classical physics, observation is a neutral act. It doesn't affect the system being observed. But in quantum mechanics, observation is an integral part of the system. It's not just about passively recording what's happening, it's about actively shaping the reality we perceive. And it makes you wonder, what else are we missing? What other quantum phenomena are lurking just beneath the surface of our everyday experience, waiting to be discovered? The implications extend beyond just quantum computing and fundamental physics. The quantum Zeno effect raises profound questions about the nature of time, causality, and the role of the observer in the universe. Does time itself flow differently at the quantum level? Does the act of observation create reality or simply reveal it? These are questions that continue to puzzle and inspire physicists today. Further examination revealed something even stranger. Nobody saw this coming. And I mean, nobody. It's called the measurement problem, and it's one of the biggest, most persistent paradoxes in quantum mechanics. It basically boils down to this. Quantum mechanics describes the evolution of systems as a smooth, continuous process governed by the Schrödinger equation. But when we make a measurement, that smooth evolution seems to collapse into a single, definite outcome. Think about Schrödinger's cat. Before we open the box, the cat is supposedly in a superposition of being both alive and dead. But the moment we open the box and look, that superposition instantly collapses, and we see the cat as either definitively alive or definitively dead. But how does that collapse happen? What is it about the act of measurement that forces a quantum system to choose one state over another? This is the heart of the measurement problem. Let's examine this a little closer. Quantum mechanics is incredibly successful at predicting the probabilities of different outcomes. It can tell you the likelihood of finding an electron in a particular location, or the probability of a radioactive atom decaying within a certain time. But it doesn't tell you which outcome will actually occur in any given instance. It only gives you probabilities. And that's where the problem arises. If quantum mechanics is a complete description of reality, then shouldn't it be able to tell us exactly what will happen, not just the odds? Why does measurement seem to introduce an element of randomness and uncertainty that isn't there in the underlying equations? One popular interpretation, the Copenhagen interpretation, essentially says, don't worry about it. Just accept that measurement causes collapse and focus on using quantum mechanics to make predictions. It's a pragmatic approach, but it doesn't really explain anything. It just sweeps the problem under the rug. Another idea is the many worlds interpretation, which is definitely out there. It proposes that every quantum measurement causes the universe to split into multiple universes, one for each possible outcome. In one universe, Schrödinger's cat is alive. In another, it's dead. And so on. So, there's no collapse, just a continuous branching of reality. It's a wild idea, and it avoids the measurement problem by essentially multiplying the universe into infinite copies. But it also raises a whole host of new questions. Are these other universes real? Can we ever interact with them? And what does it even mean for a universe to split? Then there's the idea of objective collapse theories. These theories modify the Schrödinger equation to include a mechanism that causes wave function collapse to occur spontaneously, regardless of whether or not a measurement is being made. These theories typically involve introducing new physical fields or constants that are not present in standard quantum mechanics. The hope is that these new elements would trigger collapse when a system reaches a certain level of complexity or size. The problem? No one has ever detected these new fields or constants, and these theories often struggle to reproduce all the successes of standard quantum mechanics. Consider what measurement actually means in the quantum world. It's not just about a conscious observer looking at something. Measurement can occur whenever a quantum system interacts with a macroscopic object, like a detector. But what distinguishes a macroscopic object from a quantum system? Where do we draw the line? Is a single atom a quantum system? What about a molecule? A grain of sand? A cat? There's no clear dividing line, and that's part of the problem. The boundary between the quantum and classical realms is fuzzy, and we don't really understand how the transition from one to the other occurs. The measurement problem isn't just an abstract philosophical puzzle. It has real implications for our understanding of the universe. It touches on fundamental questions about the nature of reality, the role of the observer, and the limits of scientific knowledge. And it highlights the fact that, despite all our progress in physics, there are still some very big, very basic things that we don't understand. Scientists discovered that the problem might not even be with the theory of quantum mechanics, but with our fundamental assumptions about reality itself. The implications extend far beyond the lab. If the many worlds interpretation of quantum mechanics is correct, then every quantum measurement causes the universe to split into multiple universes, each representing a different possible outcome. It's a concept that is easy to misunderstand, but let's examine it carefully. In one universe, Schrödinger's cat lives. In another, it dies. In still others, it might cough up a hairball or develop a sudden craving for tuna. The number of universes grows exponentially with every quantum event. This isn't just some abstract philosophical idea. It's a direct consequence of the Schrödinger equation, the fundamental equation that governs the behavior of quantum systems. If the wave function never collapses, then all possible outcomes of a quantum measurement must exist in some sense. The question, of course, is whether these other universes are real. Do they exist in the same way that our universe exists? Can we ever interact with them? Many worlds proponents argue that these universes are just as real as our own. They exist in a higher dimensional space, branching off from each other at every quantum event. We can't interact with them because they are causally disconnected from our universe. Each universe has its own set of physical laws and constants, its own history and future. It sounds like science fiction, and in some ways it is. But the many worlds interpretation has some compelling arguments in its favor. It elegantly solves the measurement problem by eliminating wave function collapse. It also provides a natural explanation for quantum entanglement, the phenomenon in which two particles become linked together in such a way that they can instantaneously affect each other even when separated by vast distances. If every quantum measurement causes the universe to split, then entangled particles are simply correlated in different universes. When we measure the state of one particle, we are also instantaneously measuring the state of its entangled partner in all the other universes. Consider this. What does it even mean for a universe to split? The many worlds interpretation doesn't really provide a clear answer. It simply postulates that the universe branches into multiple copies of itself at every quantum event. But what is the mechanism that causes this branching? What are the physical properties of these other universes? Critics of the many worlds interpretation point out that it is unfalsifiable. There's no way to prove or disprove its existence because we can't interact with these other universes. It's also incredibly wasteful. It requires the creation of an infinite number of universes for every quantum event, even though only one of those universes will ever be observed. Is it possible that all these universes exist, but they're governed by slightly different physical laws? Imagine universes where gravity is slightly stronger, or the speed of light is slightly slower. The possibilities are endless. The many worlds interpretation also raises profound questions about free will. If every possible outcome of a decision exists in some universe, then are we really free to choose? Are our actions predetermined by the laws of quantum mechanics? Or is there some element of randomness or chance that allows us to make genuine choices? Consider the implications for our understanding of time. In the many worlds interpretation, time is not a linear progression from past to future. It's a branching tree of possibilities, with each branch representing a different universe. The past is fixed, but the future is open and uncertain. This raises the possibility of time travel, or at least the ability to move between different universes. If we could somehow find a way to navigate the branching tree of possibilities, we could potentially travel to a universe where the past is different from our own. Of course, this is all highly speculative. We don't even know if the many worlds interpretation is correct, let alone whether time travel is possible. But it's a fascinating idea to consider. Measurements showed that the math works at least. The equations of quantum mechanics do not require wave function collapse. The Schrödinger equation marches on, unperturbed, creating a vast, ever-expanding multiverse. Whether that multiverse is real or simply a mathematical construct remains one of the greatest mysteries of science. The idea of infinite possibilities also begs the question: if there are infinite universes, does that mean every possible thing exists somewhere? A universe where pigs fly? A universe where you're the supreme ruler of Earth? A universe where cats and dogs have switched roles? It's tempting to get carried away with speculation. Many worlds forces us to confront the limits of our understanding. We are used to thinking of the universe as a single, unique entity. The many worlds interpretation challenges this assumption, suggesting that our universe is just one of many, each equally real and equally valid. The analysis continued, but the questions remain. Does the many worlds interpretation offer a complete picture of reality? Or is there something fundamental missing from our understanding of the quantum world? You've probably heard the word quantum and thought, oh, that's physics, and mostly you'd be right. But what if I told you quantum mechanics wasn't just some abstract theory for physicists, but that it played a crucial role in something far closer to home, like inside your own body? That's the burgeoning field of quantum biology. It explores the possibility that some of life's most fundamental processes rely on quantum phenomena. We're talking about things like photosynthesis, bird migration, and even our sense of smell. Processes we thought we understood, but now we're seeing there's a whole quantum layer underneath. Consider photosynthesis, the process by which plants convert sunlight into energy. For years, scientists believed that energy from sunlight traveled along a single, well-defined path within the plant's cells. But then, experiments started suggesting something much stranger. It appeared the energy was exploring multiple paths simultaneously, a classic example of quantum superposition. It's as if the energy is saying, I'll try every route at once and then pick the best one. This quantum shortcut allows plants to convert sunlight into energy far more efficiently than would be possible with classical physics alone. We're talking near-perfect efficiency. Here's what's wild. This isn't just some theoretical possibility. Scientists discovered this by using techniques like two-dimensional electronic spectroscopy, which allows them to track the movement of energy within molecules in real time. The data reveals these quantum effects in action. And photosynthesis is just the beginning. Consider the European robin, a bird famous for its incredible migratory abilities. How does it navigate across thousands of miles, often returning to the exact same spot year after year? For a long time, it was a mystery. The evidence shows that robins have a quantum compass in their eyes. This compass relies on a phenomenon called quantum entanglement, where two particles become linked together in such a way that they share the same fate, no matter how far apart they are. In the robin's eye, light interacts with certain molecules to create entangled pairs of electrons. These entangled electrons are sensitive to the Earth's magnetic field. By measuring the subtle changes in the entanglement caused by the magnetic field, the robin can determine its orientation and navigate with incredible precision. It's using quantum mechanics to find its way home. The implications extend even further. Our sense of smell, something we often take for granted, might also have a quantum basis. The conventional explanation is that we smell things because odor molecules bind to receptors in our noses, triggering a signal to the brain. But this explanation doesn't account for the fact that molecules with very different shapes can sometimes smell the same, while molecules with similar shapes can smell completely different. A new theory suggests that our sense of smell relies on quantum vibrations. According to this theory, odor molecules have specific vibrational frequencies, and these frequencies determine how they interact with receptors in our noses. It's like a quantum lock and key. Only molecules with the right vibrational frequency can unlock the receptor and trigger the signal to the brain. This quantum theory of smell could explain why some molecules smell similar despite having different shapes. If they have similar vibrational frequencies, they'll activate the same receptors. Now, you might be asking yourself, how can something as delicate as quantum entanglement survive in the warm, wet, and chaotic environment of a living cell? Quantum mechanics is notoriously fragile. It doesn't like noise or interference, and a cell is basically a noisy, interfering environment. That's the million-dollar question. Scientists are still trying to figure out how living organisms can protect these quantum effects from decoherence, the process by which quantum superposition and entanglement break down. One possibility is that certain proteins act as quantum shields, protecting the delicate quantum states from external disturbances. Another possibility is that these quantum effects are only fleeting, but that even these brief moments are enough to influence biological processes. It's also worth noting that these quantum effects aren't necessarily unique to living organisms. Quantum mechanics governs the behavior of all matter, living or non-living. The difference is that living organisms may have evolved ways to harness these quantum effects for their own benefit. It's like discovering that your car engine isn't just burning gasoline, but also using some subtle quantum trick to squeeze out a little extra power. It wouldn't change the fundamental laws of physics, but it would change our understanding of how car engines work. Quantum biology is still in its early stages, and many of its claims are still being debated, but the potential implications are enormous. If we can understand how living organisms use quantum mechanics, we could develop new technologies inspired by nature, such as more efficient solar cells, more accurate sensors, and even new types of computers. Further examination revealed something profound. Life isn't just a collection of chemical reactions. It's a quantum symphony, a delicate interplay of particles and waves, probabilities and possibilities. The future isn't binary, it's quantum. We've spent this entire time looking at the ways quantum mechanics has blown apart our classical understanding of the universe. But what if we could use these bizarre phenomena? That's where quantum computing comes in. Classical computers, the ones we use every day, store information as bits. Each bit is either a 0 or a 1. Think of it like a light switch. It's either on or off. Quantum computers, on the other hand, use qubits. Qubits, thanks to superposition, can be both 0 and 1 at the same time. It's like that light switch being both on and off simultaneously. This allows quantum computers to explore a vast number of possibilities all at once, something classical computers simply can't do. Consider a maze. A classical computer would have to try each path one by one until it finds the exit. A quantum computer, however, could explore all the paths simultaneously, finding the exit much faster. The potential applications of this are staggering. Let's examine drug discovery. Designing new drugs involves simulating how molecules interact. These simulations are incredibly complex, even for the most powerful supercomputers. Quantum computers could perform these simulations much more efficiently, leading to the discovery of new and more effective drugs. Or consider materials science. Developing new materials with specific properties like high strength or superconductivity is another computationally intensive task. Quantum computers could help us design materials with unprecedented properties, revolutionizing everything from construction to energy storage. Then there's cryptography. Many of the encryption methods we use to secure our data rely on the fact that certain mathematical problems are very difficult for classical computers to solve. Quantum computers, however, could potentially break these codes, threatening the security of our online communications. But this also means quantum computers could develop even more complex encryptions that even they can't break. This has led to a race to develop quantum-resistant encryption algorithms. The goal is to create codes that are difficult for both classical and quantum computers to crack, ensuring the security of our data in the quantum age. Building a quantum computer is an enormous engineering challenge. Qubits are incredibly fragile and easily disturbed by their environment. Maintaining the delicate quantum states required for computation requires extremely low temperatures and precise control over electromagnetic fields. One of the most promising approaches to building quantum computers involves using superconducting circuits. These circuits, cooled to temperatures near absolute zero, exhibit quantum mechanical properties that can be used to create qubits. Another approach involves trapping individual ions or charged atoms using electromagnetic fields. These ions can be manipulated using lasers to perform quantum computations. Each approach has its own advantages and disadvantages, and it's still unclear which technology will ultimately prevail. But the progress in recent years has been remarkable. Companies like Google, IBM, and Microsoft are investing heavily in quantum computing research, and they've already built prototype quantum computers with dozens of qubits. These machines are still far from being able to solve real-world problems, but they represent a significant step towards the future of quantum computing. Quantum computing isn't just about building faster computers. It's about building a fundamentally different kind of computer, one that can solve problems that are impossible for classical computers. It's about unlocking new possibilities in science, technology, and medicine. It's a completely new paradigm. The implications extend far beyond just faster calculations. Imagine optimizing logistics on a global scale, designing personalized medicines tailored to an individual's genetic makeup, or developing artificial intelligence algorithms that can learn and reason in ways that are currently unimaginable. Quantum computing could revolutionize these fields and many others. And then there's the potential for unforeseen breakthroughs. The history of science is filled with examples of technologies that were initially developed for one purpose, but later found applications in completely unexpected areas. Quantum computing could very well follow a similar path, leading to discoveries that we can't even imagine today. It's a field brimming with promise, but also with challenges. The journey to build a truly useful quantum computer will be long and arduous. There are still many technical hurdles to overcome, and it's unclear when or even if quantum computers will become a mainstream technology. But the potential rewards are so great that the effort is undoubtedly worth it. Quantum computing represents a new frontier in science and technology, a frontier that could transform our world in profound ways. Meanwhile, as the hardware develops, so must the software. Quantum algorithms are fundamentally different from classical algorithms. They require new programming languages and new ways of thinking about computation. Developing these algorithms is a major area of research in quantum computing. Scientists are exploring new quantum algorithms for a wide range of problems, from optimization and machine learning to materials science and drug discovery. One of the most famous quantum algorithms is Shor's algorithm, which can factor large numbers much faster than any known classical algorithm. This algorithm has the potential to break many of the encryption methods used to secure our online communications, highlighting the importance of developing quantum-resistant cryptography. Another important quantum algorithm is Grover's algorithm, which can search unsorted databases much faster than any classical algorithm. This algorithm has applications in a wide range of fields, from data mining to artificial intelligence. The development of quantum algorithms is still in its early stages, but the progress has been rapid. As quantum computers become more powerful, we can expect to see even more sophisticated quantum algorithms emerge, unlocking new possibilities in science and technology. The quantum revolution is not just about understanding the bizarre laws of the quantum world. It's about harnessing these laws to create new technologies that can solve some of the world's most pressing problems. It's about building a future where the impossible becomes possible. It's about harnessing the very fabric of reality to create a better world. Scientists discovered something truly exceptional: 0.01. That's the percentage of the universe that we actually understand. It's a pretty humbling thought, isn't it? The quantum experiments we've been talking about, the double-slit experiments, quantum entanglement, quantum tunneling, these aren't just abstract concepts cooked up in some ivory tower. They're glimpses into the true nature of reality. They're pointing us towards a deeper understanding of how the universe works, even if that understanding is still frustratingly incomplete. And incomplete it is. We've built incredible technologies based on quantum mechanics, lasers, transistors, medical imaging devices, and now, potentially, quantum computers. But even with all these successes, we're still scratching the surface. We still don't fully grasp the implications of quantum mechanics or how it connects to other fundamental forces like gravity. Consider the problem of quantum gravity. General relativity describes gravity as the curvature of space-time, while quantum mechanics describes the behavior of matter and energy at the smallest scales. These two theories are incredibly successful in their respective domains, but they clash when we try to combine them. We simply don't have a working theory that can reconcile general relativity and quantum mechanics. This is one of the biggest open problems in physics today. Some promising approaches include string theory and loop quantum gravity, but these are still very much works in progress. The implications extend far beyond the theoretical realm. A theory of quantum gravity could revolutionize our understanding of black holes, the Big Bang, and the very nature of space-time itself. It could also lead to new technologies we can't even imagine today. And then there's the measurement problem. Quantum mechanics tells us that particles can exist in multiple states simultaneously, a phenomenon known as superposition. But when we make a measurement, the particle collapses into a single, definite state. The question is, why? What constitutes a measurement? Does it require a conscious observer? Does the act of observation somehow force the particle to choose a single state? These questions have puzzled physicists for decades. Some interpretations of quantum mechanics, like the many worlds interpretation, propose that the universe splits into multiple parallel universes every time a quantum measurement is made. In each universe, the particle exists in a different state. This may sound like science fiction, but it's a serious attempt to grapple with the measurement problem. Further examination reveals that even the seemingly simple act of measuring a quantum system is fraught with philosophical and practical challenges. The more we learn, the more we realize how much we don't know. The analysis continued. Scientists began exploring the connection between quantum mechanics and consciousness. Some researchers believe that consciousness plays a fundamental role in the collapse of the wave function. Others are skeptical, arguing that consciousness is simply a product of complex brain activity and has no bearing on quantum mechanics. The debate is far from settled, but it highlights the profound implications of quantum mechanics for our understanding of ourselves and our place in the universe. Meanwhile, new experiments are constantly pushing the boundaries of our knowledge. Scientists are exploring quantum effects in increasingly complex systems, from large molecules to living organisms. They're developing new techniques for manipulating and controlling quantum states, paving the way for new technologies. One of the most exciting areas of research is quantum biology. This field explores the role of quantum mechanics in biological processes, like photosynthesis, enzyme catalysis, and even bird navigation. The idea is that quantum effects may be essential for life as we know it. The implications are astounding. Consider photosynthesis, the process by which plants convert sunlight into energy. Scientists have discovered that plants use quantum coherence to efficiently transport energy through their light harvesting complexes. This suggests that quantum mechanics plays a crucial role in the efficiency of photosynthesis and could potentially be harnessed to develop more efficient solar energy technologies. And let's not forget the ethical considerations. As quantum technologies become more powerful, we need to think about the ethical implications. Quantum computers could break encryption algorithms, threatening the security of our online communications. Quantum sensors could be used for surveillance, raising concerns about privacy. It's crucial that we have open and honest conversations about these ethical issues and develop guidelines and regulations to ensure that quantum technologies are used responsibly. Scientists discovered that the quantum revolution is far from over. It's an ongoing process of discovery, exploration, and innovation. It's a journey into the unknown, a quest to understand the deepest mysteries of the universe. The weirdness of the quantum world challenges our intuitions and forces us to question our assumptions about reality. It reveals a universe that is far stranger and more wonderful than we ever imagined. The unfinished revolution? It's a wild ride, and the best is yet to come. If you enjoyed this deep dive, hit that subscribe button for more explorations of the cosmos and the quantum realm.